Welcome back! So in this video we're going to talk about where the derivatives of the trig functions come from, specifically where the derivatives of sine, cosine, and tangent come from. So we're just going to look at the graphs in order to do this. So let's start with sine. So to find the derivative of sine, let's first graph the function f of x equals sine x and ask ourselves some questions. So first, where is the derivative 0? So looking at the graph, the derivative will be 0 where the function has a horizontal tangent line, or where we have local maximums or minimums. So I'm seeing that we have a derivative of 0 at pi over 2, 3 pi over 2, 5 pi over 2, negative pi over 2, negative 3 pi over 2, and negative 5 pi over 2. So I'm just marking these locations here, and then when we go look at the graph of the derivative below, we're going to indicate that the derivative is 0 at those points as horizontal intercepts. So the output at those input values is 0, so at pi over 2 the output is 0, 3 pi over 2 the output is 0, etc. So we know the derivative will have points at these locations. Next we can ask, where is the derivative positive? So this is where the slope of sine is positive. So on our portion of the graph here, the slope is positive from negative pi over 2 to pi over 2, from 3 pi over 2 to 5 pi over 2, and from negative 5 pi over 2 to negative 3 pi over 2. So on our graph of the derivative, we know that the derivative will be above the x-axis here, and that's because the outputs need to be positive in order to correspond with an increasing function. So if the function's increasing, the derivative is positive, so the outputs on the derivative graph have to be positive. Then we can ask ourselves a similar question for a negative. So the derivative is negative when the function is decreasing, and so sine is decreasing from negative 3 pi over 2 to negative pi over 2, and from pi over 2 to 3 pi over 2, at least on our portion of the graph here. So we know that the derivative will be below the x-axis in these intervals. The outputs have to be negative for the derivative because the function is decreasing there. It has a negative derivative. So to help us get some more points that are on the graph of the derivative, let's look at x equals 0 on our regular function sine. So if we look at 0, the slope here is 1. You kind of have to take my word for it, but you can imagine if we zoomed really far in, the graph would have that perfect diagonal slope of 1, and so we are saying that the slope or the derivative at x equals 0 is 1. So that corresponds to the point 0, 1 on the graph of our derivative. We can do the same thing for the points that have the same slope, so at 2 pi and at negative 2 pi. Now we can do the same thing at pi, so at pi the slope is negative 1. So on our graph of the derivative, the output will be negative 1 at pi. Then I can draw in the point at negative pi where the slope is the same, the derivative or the slope is also negative 1 there. Then I can connect the dots and draw my graph of the derivative. Now, okay, you should be thinking, hey, this looks like something else I know, and in fact it is. So the derivative here is cosine. This is the graph of cosine. So in fact, the derivative of sine is cosine. This is one of those things in math that whenever I have to think about it, just completely blows my mind. We have this graph of sine, and its derivative, the function that represents the slope at every point on the function, is cosine. It just seems so convenient and beautiful. I love it. Okay, let's repeat this for cosine and see what we get. I'm excited. Hope you're excited. Okay, so let's say g of x is cosine, and we're going to find g prime of x. And we're going to start by asking the same questions. So first, where is the derivative 0? I'm going to mark those locations here. Again, it's where the slope is 0, so you can imagine it's where the function changes from increasing to decreasing, or vice versa. Then I can mark these locations as horizontal intercepts on the graph of my derivative, places where the output is 0 since the output is the slope. Then I can ask, where is the derivative positive? The derivative is positive from pi to 2 pi, from negative pi to 0, and from negative 3 pi to negative 2 pi. So on my graph of the derivative, these are locations where the derivative is above the x-axis, it's positive. Similarly, the derivative is negative when the function cosine is decreasing. This is from 0 to pi, from 2 pi to 3 pi, and from negative 2 pi to negative pi. So these intervals are where the derivative is below the x-axis. It has a negative output. So I'm going to follow a similar train of logic as we did with sine. If we look at the points where the slope is either positive 1 or negative 1, we can add in those points to correspond. So for example, at pi over 2, the slope is negative 1, so that's an output of negative 1 on the derivative. So we can connect the dots, and we see that this is actually negative sine of x. That negative means we've reflected it over the horizontal axis. So instead of going up as it goes to the right, it goes down as it goes to the right, starting at the origin. So this is a reflection of sine. It's negative sine of x. This means the derivative of cosine is negative sine. Alright, so to wrap up this video, I just want to talk about the derivative of tangent. So for the derivative of tangent, I'm just going to tell you what it is first, and then we're going to make sense of it using the graph. So if f of x equals tangent of x, then f prime, the derivative, is secant squared of x. I'm also going to just write this using the other notation, so the derivative with respect to x of tangent is secant squared. So what does this look like? Why does this make any sense at all? So let's look at the graph. I've graphed tangent here and secant squared. So the tangent graph is something we're probably used to seeing, but the secant squared graph is different. It might not be something we've ever seen before. But let's look at the tangent graph. So tangent is always increasing where it's defined. It has vertical asymptotes at pi over 2, 3 pi over 2, etc. But everywhere in between those vertical asymptotes, the function is increasing. So if tangent is always increasing, its derivative is always positive. So this means our derivative graph is going to be entirely above the x-axis. Also, since tangent is undefined at pi over 2, 3 pi over 2, etc., this means its derivative is also undefined here. So it makes sense that our graph of secant squared has vertical asymptotes at the same values as tangent does. Let's just look at one more place on the graph of tangent just to make sense of its derivative. So let's look at x equals 0. So coming into 0, the function tangent is very steep. It levels off a little bit, and at that 0 point, it actually has a slope of 1. Again, you kind of have to take my word for it, but then after 0, it becomes steep again. So a steeper slope corresponds to outputs that are further away from the x-axis. Then the slope of 1 at 0 means the output will be 1 at that point. Alright, hopefully this is enough for you at least to believe that secant squared is an appropriate derivative for tangent. Awesome, well that is it for this video. Thank you so much for watching, and I will talk to you in the next one.